Okay, perfect. So welcome everybody to this new IPARCOS astro-seminar. Today it is a pleasure to introduce the speaker, which is Luca Costantin. Luca got his PhD in 2018 at the University of Padua, working under the supervision of the Professor Corsini and Dr. Jairo Mendez-Abreu on observed properties of bulges in the local universe. He then joined the WIF STEPS collaboration and moved to the Observatory of Brera in Milano to work with Angela Lovino, which is the PI of the survey. After that, he got the Atracción del Talento Fellowship and joined Pablo Pérez González in the Centro de Astrobiología. Pablo is the PI of the SHARDS survey. And now Luca is a research associate on the MIRI High Redshift Science Group and the CERS Early Release Science Program for the James Webb Space Telescope. This together with being still a Atracción del Talento Fellowship. So Luca, probably I missed many things you are involved with. If you want to add something else, please don't hesitate. And if not, you can start as soon as you want. And again, thank you for accepting the invitation to present your work here in the IPARCOS astro-seminar. Luca, we cannot hear you. You are muted.
Yeah, sure. Thank you, Santi, for your words. So today I'm here to talk to you about massive disk galaxies, and in particular, which is the morphological evolution of massive disk galaxies. And I will present the latest result that we obtained as part of the SHARDS team. And I like to acknowledge particularly Pablo, Jairo, and Mark that make this possible, and all the SHARD collaboration, of course. So this is the outline of my talk. I will start just introducing a bit galaxy morphology, in particular, which is the evolution of different structure through time, focusing on galaxies and on their structures. Then I will introduce a technique that was recently developed to separate bulges and disks in galaxies. And then I will start presenting my later result. The first one is about the bulge population, and the second one is about the disk population. And then if I still have some spare minutes, I just say a few words about what's coming in the near future for galaxies. And importantly, we are in a good time and place today to look at the Hubble tuning fork, not only for today's galaxy, for the local universe, but also to see how this tuning fork evolved through time. And this is true for observation, but it's also true for numerical simulation, because nowadays numerical simulation are able to reproduce and to mimic galaxy interaction and the physics behind this interaction with a level of detail that a decade ago was unthinkable. So yeah, I will show just a few examples of galaxies where you can see on the left part the gas distribution, on the right part the stellar mass distribution of this bunch of galaxies from the TNG fifth suite cosmological simulation. These are galaxies at redshift 2, and you can see the level of detail that also in numerical simulation we can reach. So knowing this, that we can observe and also from in our laptop from a numerical simulation, but also on the sky, this structure on galaxies, I like to start stating three basic things that we know about galaxy evolution. The first one is when the stars in galaxy form. So this is the well-known evolution of the cosmic star formation. So this cosmic star formation as a function of look-back time, and we know that the peak of star formation, so the bulk of stars in galaxies form between redshift 1 and 3 and peak a redshift more or less of 2. So this is true when we look at galaxies in general, but we may start asking ourselves, are these stars forming in the central region of the galaxies? Do we know if they form in the outer region of the galaxies? And probably, does it really matter? Is this important to know? Or we are fine with what we know? The second thing that I like to comment on is, so we know when the stars form in galaxies, But then we know that also galaxies stop forming stars. So at redshift 2, I said that galaxies are more or less, or the bulk of the galaxies are start forming. But then as time passes, a population of passive galaxies is dominating the high mass end of the stellar mass function. So we know that from redshift 2 to local universe, this passive population of galaxies is building up and is dominating. So again, we know what galaxies do and transition from being star forming to passive in a process called quenching. But then again, in which region of the galaxies does this star formation stop? And more importantly, could the star formation start again, or is just a process that stops and then never start again? And then is it a fast or slow process? So as you see, I'm dropping questions throughout this introduction, and let's see if we can have some answers later on. The first statement is about the evolution of size of galaxies. This is a well-known fact, and here I'm showing the mass size relation from Van der Waals 2014. And you can see in this plot from the top left to the bottom right, different bin or redshift, and you can appreciate the evolution in size of galaxies, meaning that at higher redshift, galaxies appear more compact. So we kind of know, and this cartoon explains which is the evolution of a galaxy which in this plane. So when a galaxy is star forming, is mainly grown by the star formation, is mainly growing in mass. When the galaxy reach threshold mass, it quenched, and when it's quenched, its evolution is mainly in size. So it's accreting in size by mergers. So one important question that we can ask ourselves is that we see that in the higher universe, in the higher redshift, we see galaxies that appear more compact, but can these galaxies that are compact develop a star forming disk at later times? The answer from simulation is yes, and these are snapshots taken from the Snyder paper where they create these images for the galaxy in the Villa simulations, and I'm showing just two examples. So you see from the right to the left, the evolution of a very compact source that that is quenched because it's quite reddish at redshift 2, and then it kind of form a disk around it, an extended stellar disk that is in place by redshift 1. So this is just to say that the structural evolution is not always monotonic in galaxies, and we have to take care of this when we are describing the evolution of the galaxy population. So these are three things that we know: when stars forming galaxy, when galaxies stop forming star, and how the size of galaxies evolves. But I hope that I pass this message that we have to take into account the studies of integrated property, but compare it with the property of the single structure of galaxies, because integrated properties are probably averaging out the complexity of the evolution of a galaxy. So just one last example about this. This is the stellar mass budget from the Gamma survey. And I'm showing here, you focus on the lower panel in this plot. This is the fraction of the total stellar mass when you model the galaxy with a single component. So each galaxy can be either a spheroid or a disk, and this is the trend of the disk versus a spheroidal total mass as a function of mass. But if we compare this plot with the Khalifa sample, where galaxies are modeled with multiple components, and you focus, for instance, on the green line, you see that at masses between 9.5 and 11, or more, 50 to 70% of the galaxies are better described with multiple components. That's why it's very important to study the different structure of galaxies. Our picture is changing a lot. So the last question that I'm dropping as are how do the spheroidal and this component in galaxy form, and in particular, is there a time where this happened, when galaxies shape their morphology? And probably more difficult to answer is that there is a physical or a parameter that is driving this evolution. So for starter, we need to separate different components, and I said, and in particular, if we look at this galaxy, we want at least to separate the bulge and the disk and study them separately, understand what's going on in these galaxies. So the spectro-photometric decomposition is a technique that was recently developed and is used to separate photometrically the galaxy light into its bulge and disk and apply this decomposition through wavelength. So this is a view that we have, that something that everybody knows. This is a data cube, and data cube is just a collection of images at different wavelengths. So if you focus on a single wavelength, we have an image of the galaxies at that wavelength, but this is not the true story, because if you go in one pixel in the 2D image and we go across wavelength, we have the spectrum at that position of the galaxy. So the 2-point of view across wavelength means that if an ideal case, we would like to have for every galaxy in the sky a very high signal to noise data cube, which will allow you for each single wavelength to perform a photometric decomposition, meaning that you can model at each wavelength the light of the galaxy into its component. And then this, again, is not the true story, because once you model the light of the galaxy and you separate the two components, you can go in each single pixel again and have a spectrum of each bulge and disk in each pixel of the data cube. But of course, we have to face reality. We are not in ideal case. So the reality is not having this very high signal to noise IPU data. So the solution that I took in this study is starting from broadband images, which provide the high spatial resolution that allow me to understand and constrain better the structure of galaxies, perform a photometric decomposition, so modeling the galaxy light into its component, and then freeze the structure of the galaxies and repeat this to the photometric decomposition with a new data set that provide a better spectral resolution than broadband images. And this allows you to have a spectral energy distribution for the separate bulge and this component. So to do so, I use the SHARDS dataset that is ideal for this kind of study. SHARDS is a survey-for-ized absorption redundant sourcing by Pablo Pérez González. Is an ISO-ZTC large program that was aimed to target the Gauss-Nord field, and is very important on this kind of study because it provides very deep photometry in 25 continuous filter from 0.5 to 0.95 micron. We provide a spectral resolution of more or less 50. So this is for the spectral resolution, and for the spatial resolution, of course, I went to HST image, and here I'm showing in the upper panels an RGB composed image and 3 different filters for HST data for the galaxy with candles ID 18522. That will be our test galaxy for this talk. And I compare it with the SHARDS data. So you can see the difference in the spatial resolution of the 2 images, but I have to remind you that the spectral resolution provided by SHARDS, you will see, is the one that is doing the job here. So when I talk about photometric decomposition, this is an example of it. So this is the H-band filter for HST, and we have our galaxy, and we focus on the right panels. On the top, we have the galaxy itself, the image, and then on the middle panel, we have the model of the galaxy. So the galaxy was modeled with the GAUSS-2D algorithm, and you can see an example of the ellipse average radial profile on the left panel. where you have the data point in black and the model of the galaxy is the green line. That is the sum of a bulge and this component. So this is just one wavelength, as I told you, mainly a broadband, so a collection of wavelength. And then we have to transfer this information of all the shared images. So here what I do again is just I froze the structure of the galaxy, meaning the structural parameters like the ellipticity, the position angle of the different bulge and disk. And then I allow the intensity to vary across wavelength. So what here we are really doing is just obtaining for each galaxy this kind of bulge over total or bulge over disk light ratio as a function of wavelength. So from each of the 25 medium band SHARDS filters, I obtain one of these points that are the yellow diamond. So you see the fraction of light of the bulge and disk is varying across wavelength, and I like to focus your attention on one particular point. This point is telling you that comparing to the nearest filter, the bulge light is less prominent than the disk light in this particular wavelength. And this is the wavelength where oxygen light are present. And I remember you the oxygen light, we associated them with disk structure. So you see here that the decomposition is doing its job. So it's time to talk about results and see how this apply to a sample of galaxy, not just one example. So the sample of galaxy is a sample in Gauss-Nord field. These are the galaxies that are between redshift 0.1 and 1, and are more massive than 10 to the 10 solar masses. And in particular, I will focus on the distribution that is in red. That is a sample of 91 disk galaxies, meaning that these galaxies were modeled with two components, a bulge and a disk. So this is how these galaxies look like, and as a function of the stellar mass and the bulge over total, you see they have different morphology and different structures. So just focus about on bulges firstly, but I like to show you which is the power of having this spectral energy distribution. So I told you that I use SHARDS data combined with HST data, and then I added also the K-band for better estimation of the stellar mass. Here you have the diamond that represent the model for the bulge plus disk, means the galaxies in green. Then you have in blue the stellar disk, and in red the bulge. And then you have solid lines, and solid lines are models that are fitted to the data points. So we parameterize the star formation history, and we use Brussels stellar population library with sub-initial stellar mass function and different beams of metallicity. And these are the best fit for each single component and the galaxy as a whole for this galaxy. From stellar population, we can retrieve parameters that are used to understand the single components, how they evolve. And here I'm showing you mass-weighted edges of the bulge component. So I like you to focus on the red part of the histogram and the data points. So this is mass-weighted edges as a function of stellar mass. And the first fact that I highlight here is that there is an increasing trend with mass, meaning that the more older a bulge is, the massive it is. And the second fact that is very, very important is that there is a bimodal distribution of bulge edges, meaning that half of our sample has mass-weighted edges greater than 3 gigayears with an average value of 6.3, and half of the sample have edges that are less than 3 gigayears with an average value of 1.8. But I told you that our galaxies are in a wide redshift range. So to be fair, we need to compare formation redshift. So we translate these mass-weighted edges to the corresponding redshift, and this is what's happened. So you see that the trends remain. So again, the bulges that form first are the more massive, And also the bimodal distribution is true and not an artifact of having different ranges for the galaxies. The number changes a bit. So 1/3 of the galaxy are really forming at very high redshift, and 2/3 of the galaxy are forming a lower redshift. So we identified these two waves of bulge formation, and we called the first one first wave bulges, the one that form a higher redshift, and a second wave of bulges forming a lower redshift. But which are the properties of those bulges? So I'm a bit spoilering here in the title where we are going. This is again mass size plot for our bulges, and I'm plotting here with the dashed line the trends from the Van der Waal paper. So in blue you have the trend for late type galaxies, and in red you have the trend for early type galaxies. And you immediately see that bulges more or less are behaving like early type galaxies. But then if you just pay attention of the color coding, you see that the bulges that form a higher redshift appear to be more massive. So this one here, so the one that form a higher redshift. So we have a better look at this kind of structure, and here I'm showing the mass surface density plot, so that you have in the y-axis. So it's a proxy for the compactness of the galaxies as a function of the stellar mass. And again, if you focus on this upper right hand, you see that the more compact objects and the more massive are the ones that form a higher redshift. And we identified these first wave bulges as red-nugget relics that develops at this later times. So to understand what's going on, I try to make up this cartoon. So we think that very high redshift, there are violent disk instability that trigger a funnel gas into their center and lead to a phenomenon compaction to what is observed as a blue nugget, and we identify a fourth wave bulges. As time passes, the star formation in this structure stops, and this is observationally seen as a red-nugget at the redshift of 2-ish. But then at some point that this grow, and we see this later on, and then we remain with a massive disk galaxies with a relics in its center that is what we call a first wave bulge. So you here have the same kind of picture, what's happening for the first and second wave bulges. And I like just to comment one fact about this cartoon again, that is the difference in the intensity of the star formation episode that from first and second wave bulges. So you can see in the middle panel where there is star formation rate is the function of redshift, the difference where first wave bulges have a very, very, very intense episode of star formation at redshift. And the second fact is that first wave bulges form in a fast way, meaning that the time scale of their formation is very fast, while for second wave bulges also a slower mode come into place. So we mainly understand how bulges are forming, and there are two waves of bulges, and the first wave are characterized from being very, very compact as red-nugget relics. But what's happening for the disk? So I will show you some preliminary result that we obtained recently about the disk evolution. So this is the mass assembly history of our structure in the 91 galaxies. So on the left you have bulges, on the right you have disk. I know that is a busy plot, but I like to focus your attention on two particular things. So just to explain a bit the plot, the first thing to know is that there is a solid line. So the solid line is our galaxy evolve, our structure evolve in this plane. So from forming 10% to its mass to the 90% of its mass, going from left to right. And then the star are where the bulge or the disk is growing 50% of its mass. The first things to notice is that very, very high redshift, we already mentioned that are the first wave of bulge that forms, but you see there are only few disks that are growing out very high redshift. The main difference, as I told you before, bulges assemble very rapidly, but these disks are growing more slowly. And the second things that you can focus is the first versus second wave formation of bulges, while for this, it seems that from redshift 1-ish is the disk era. So the disks are forming consistently around the first and second wave bulges, but starting from redshift 1.5, more or less. We can see it again, looking at the average star formation history of the two component. Again, is a busy plot, but I want you to focus on the 4 morphological epochs that we found in the evolution of these massive galaxies. So again, the first wave bulges formed with a very high and intense episode of sun formation. The first disks start to form with a time delay and are characterized by a lower episode of star formation and of longer time scales. Then there is the epoch where second wave bulges are assembling, and then the disk era starts from redshift 1. And just to compare with the result that I used to show you at the beginning, this is the formation redshift or half mass redshift for both bulges and disks, where you can appreciate that the distribution of bulges is bimodal, and the one of disk is not. And you can also appreciate the histogram that is showing the distribution of the half mass ratio of disk is just saying that disks are forming a lower redshift than bulges. This is true in general, but what's happening galaxy by galaxy? So we had a look at this, and here I'm showing you the age difference between the mass-weighted ages of the bulge and the disk. So again, this is not telling you the true story and the old story, but it's a proxy to see which is the component that forms first. So on the y-axis, you have this age difference. So positive value means that the bulge is forming firstly. And you see that there are dashed line and dashed dotted line. So the green one is the average for the whole population of bulges. And the purple and yellow one are for the two separate components, first wave bulges and second wave bulges. So we can conclude that on average, spheroidal galaxies take 1.5 gigayears in acquiring an extended stellar disk. So we try to cross-correlate all the different parameters, morphological parameters that we have for our sample bulges and disks. And I'm showing here just the strongest relation we found. So this is again, the age different from mass-weighted ages of bulges and disks. I remember you that positive values means the bulge formed first. And this is as a function of the mass of the bulge. And are color-coded according to the bulge prominence. So BT equal 1 means a galaxy that is just dominated by a bulge. So you see that there is a positive correlation, meaning that the more massive bulges are the ones that form as this at later times. So we interpret this, and this is also very consistent with what is found in the Khalifa survey for local galaxies, that the bulge mass is regulating the timing of the stellar disk growth, and is probably driving the morphological evolution of these massive galaxies. And my last slide is just a warning. So I told you that the first one was the previous one was the strongest correlation we found, and this is just a correlation of the age difference according to the bulge searching index, where no correlation is found at all. And for instance, no correlation is found with either the bulge searching index or the galaxy searching index, and neither with this age difference or the formation of the component. So just for you to be aware when you use searching index to classify your galaxy, that probably you're not probing the evolution. So you have to be careful about it. So I think I'm in time just few more minutes for spend of what's next, the new domain for galaxy morphology, and just really a couple of slides to tell you and you probably already know that JWST is almost ready to fly. And this will open a new era for high redshift galaxies, of course. And I like to mention just two projects. The first one is what MIRI will provide. So MIRI will provide both spectral images for galaxies in the far infrared, and will provide broadband and narrowband images from 5 to 28.5 micron, with a pixel scale of 0.11 arcsecond per pixel nominal. So you understand that the depth that we will reach with MIRI observation at this resolution will allow us to see and to characterize the optical and infrared morphology of high redshift galaxies with unprecedented level of detail. So this is, of course, very exciting. And the second one is the ERS SEERS. So SEERS is the Cosmic Revolution Early Release Science, and this one of the programs that was approved and which data will be published from day one, which goal is studying the very high redshift sourcing to characterize their nature. But of course, since it's using the whole suite of JWST instruments like near-cam and MIRI imaging, near-spec and near-cam spectroscopy, of course, we will able also with this kind of data set to quantify the first bulges and the structure that are forming a very high redshift. So stay tuned. And this is the summary conclusion. And I hope I pass the message that it is very important just not to looking at the whole galaxy, but to compare its integrated property with those of the individual components, and in particular of the bulge and disk, and if we can, of bars and other structures. The first result we obtain is that the bulge evolution information is bimodal, and in particular that there is a wave, the first wave of bulges that we identify as red-nugget relics that are embedded in these galaxies. The second result is about disk, and we found that the disk era start at redshift 1, and in this sense, this is the bulge mass that is driving the time scale of the disk growth. And again, stay tuned because in almost a couple of weeks, JWST is ready to fly, and a new era is opening for the morphological evolution of these very high redshift sources. And thank you.
Great, thank you a lot, Luca, for this very nice work you are doing. I have plenty of questions as usual, but first of all, I will let the audience to ask first. So please, in the audience, you can raise your hand and I will give you the opportunity to ask. We have first one from Doris Topacher. Please, Doris, you can unmute yourself and you can start asking.
Hi, can you hear me?
Yeah, sure.
All right, okay. Hey, thank you so much, Luca, for this talk. It was amazing, really interesting, and also your graphics were amazing. My question would be, did you also look at metallicity in your galaxies by coincidence?
So when we model each structure, the set of each structure, we allow 3 binom metallicity. Mm-hmm. So the distribution in the metallicity plane is quite wide. Mm-hmm. So we aren't able to constrain so much metallicity. Mm-hmm. So we try to rely on the mass-weighted edges and masses, which are the most constrained parameter we have. To look for metallicity, we already have approved a proposal to have integral field data for some of those galaxies. So this can be really be the point to understand what's going on in the first wave bulges that I think are the most interesting. Not only metallicity, but also alpha enhancement, which will constrain time scale of formation. So yeah, so we have a lot of metallicity, but we decided not to rely on those quantities, but on mass-weighted edges, and as a follow-up, have a look at them from spectra, where we can better constrain them.
All right, thank you.
Okay, thank you, Doris. If anybody else has a question, please just raise your hand. If not, I will proceed with my own ones. Oh, okay. We have Mark Balcells. Please, you can unmute yourself and start.
Hello. Thanks, Luca, for a beautiful summary of your two papers, and also great introduction and building up the expectation for a JWST. Yeah, we are in a great era for galaxy morphology and for, as you have demonstrated, for being able to interpret galaxy morphology and infer galaxy evolution from morphology. Yeah, exciting times. My question is one that also came up for me with your recent two papers. The method involves the assumption that each component is homogeneous, right? So the bulge is one population and the disk is another population. Now this is a kind of a first bit into breaking the galaxy instead of one single galaxy, the whole thing, not just divided in two parts, inner part and another part. Now this disk, two comments. The disk will have grown inside out likely, and so the question is, can we see a gradient in its age over the disk? And the second question, more general, have you tried or have you conceived doing this analysis without doing a bulge disk decomposition, but just as a function of radius?
Okay, I start from the first one. So of course, the disk and also probably the bulge is kind of formed inside out, outside in. It doesn't matter, but it can have a gradient. So that's why what we really need as latest step is IFU data with high spatial resolution to just characterize for each single structure what's going on from the very center to the outskirt. And then, of course, it's model dependent. So we are just assuming that this galaxy is a sum of a bulge and a disk, but the disk also can be modeled as a break disk. So you can have a break at some radius, and you can probably allow for more stellar population to fit there. So of course, it's model dependent, and of course, we want to understand what's going on in the different component at different radius. And I haven't tried to look at the whole galaxies as a function of radius, but it's something that we already discussed to do. So these are the first two papers of a series, and one is about to come when we would like to compare the galaxy's properties as a whole compared to what's happened to the single structure. So for instance, another interesting is just looking UVJ diagram of those galaxies and how these galaxies are classified in UVJ diagram, but what's happening in a single component. And you can also have, as you suggest, this radial profile and looking at different radius of the galaxy what's happening. But yeah, I think this analysis that I've done is a first step, and we need to just start working into this, because it's very exciting that the result we are obtaining and looking at these different components. And I mentioned that the work in the Khalifa sample by Jairo Mendes Abreu that was also recently published, and we are obtaining a different redshift, the same picture of how these galaxies are evolving inside out and what's driving the evolution of these galaxies. So I think it's a first step, but very, very more is needed to be done. Of course, starting from the modeling and then going from very high signal to noise IFU data to really constrain. Also, as I commented before, metallicity and radial gradient of properties.
Great, thanks.
Okay, we have another question by Alexander Vazdekis. Please, you can just unmute yourself and you can start with the question.
Yeah, thank you for the nice summary of your of your two papers. I think this is really interesting stuff, and we got to the point that that we can start to distinguish the components and then perform the analysis independently, which is already telling us quite a lot, no? As you pointed out. No? And just one comment and at the same time question. No? So because I personally dislike this, let's say when we say, okay, inside, out, out, inside, I find it really confusing. I mean, what does it mean inside out or out inside? I mean, the point is that, okay, I can understand that, for example, the disk may be younger, but this is on I mean, the mean age, let's say, might be younger, okay, but it does not mean necessarily that there are stars that are as old as the bulge itself. So this is in fact the question. So on one hand, the comment that I mean, I know that many people, they like to use this terminology, but I find it confusing. It's probably not helping much in this context, you know, to when you separate the components. So can you have any comment on that?
Yeah. Thanks a lot for the comment, because I'm saying that I completely agree with you. So also when I was writing the paper on we're discussing with collaborators, I think that the terminology we are now using to describe this evolution of galaxies in general, but then is very more difficult when you go to a single component, is sometimes misleading, and I totally agree with you. And also as I told you when I was presenting it, so just say mass-weighted ages. So this is just an average value for a whole population. So it's not really telling you which is the time scale or other parameters that could influence what's going on. So that's why I said that is just the first step to understand what's going on. So we see that the average value of the population is this one, and which is the component that probably the bulk of the stars has formed first. But then you need to go into the details and see what's happening there, because the evolution of the galaxy is very more complex than what we are stating. This is my belief. So my first step is just going from the whole galaxy to each individual structure. But then when you are there, you need to discuss and just have a look at different parameters to really understand what's going on. You just cannot just compare ages. You will need at some point also metallicity. And you can also just look at average value, but we have to look at how is parameterized the star formation history. And also not just as a global properties, but spatially resolved. But I totally agree. I agree with you, and I'm sorry sometimes I was also confusing, but yeah, I agree.
I think that I mean in your case, because you are in fact deriving the star formation history, well, at least roughly, no. This is far more, let's say, telling us, okay, of what is going on, because it's not the same. I mean, saying that this, you know, in, out, out, in, whatever, you know, or yep. Say that, okay, for some reason, the star formation, let's say, efficiency or the way the stars are start to appear or to be created on the disk is on a slower pace, which does not exclude there the presence of all the stars. But then you understand the question becomes different, you know, from the, I mean, from the galaxy formation scenario. I mean, it's telling you that for some reason this component okay, it goes slower, okay, over time, no? And this is, you see, it's subtle, but it makes a difference, huge difference from the galaxy formation interpretation. Yeah, thanks. So thank you.
Thank you.
Okay, thank you. So if we have another question from the audience, please just raise your hand. If not, I have a couple. Okay, so I will start with my first one. The first one is related with the formation of bulges in the first wave. You said that your hypothesis is that in the first wave, bulges form through the violent disk instability. I agree that this one is one of the well-known mechanisms that we observe in cosmological simulations to create these spheroids. But this is also true that this competes with the mergers, with a large number of mergers that are happening at high redshift. So do you think that this is a combination of both violent disk instabilities for gas-rich disks and mergers, or maybe are two different mechanisms that produce different structures, different morphologies that you can identify at some point, or both mechanisms can produce exactly the same bulges you observe in the first wave? I don't know if you have any comment on the origin of these first wave bulges.
Yeah, so my hypothesis, since we are in the field of hypothesis, it's just probably multiple phenomena are coexisting, and this is the answer that we can get for the data that we have right now. For what we know for sure is what we observe, and these bulges are very, very compact, and they resemble the red nuggets, blue or red or whatever you call them, at very high redshift. So there should be a mechanism that can be clamp migration or the violent disk instability triggered by a lot of minor mergers of very high redshift, but something that funnel the central part, the gas in the central part, and that's produce this very, very high intense episode of star formation that shrink the galaxies. So what I can tell you that, of course, that can be multiple phenomena happening, but those phenomena have to lead to this compaction event, at least for the first wave bulges.
Okay, and the second wave are purely from mergers?
No, the second one, I haven't talked much about them. I can go back to the cartoon that I have. So the interpretation of second wave bulges is a bit more difficult because I told you that they form on similar time scale that the first one, but some of them are forming on lower, on higher time scales, meaning that the evolution is just slower. So what's going to happen here, since we are reaching the peak of the Skolnick star formation history, so some of them can form really by minor mergers. So at some point that can be a separation where some bulges just accrete in size due to the minor merger because they are really quenched. But probably the bulk of them can also be formed at lower redshift with some compaction events. So I think that for using this dataset was really hard to distinguish a single phenomenon that is taking place in the formation of these second wave bulges, because their properties are quite broad. So we haven't defined a single category, or we haven't identified them as driven by a single event of formation.
Good, thank you. And I have the second question, that one of your conclusions is that there is a dependence on the bulge mass on the rhythm that the disks are formed. Is this a dependence on the bulge mass, or is this in fact a dependence on the total galaxy mass? And this probably reflects this golden mass proposed by Deckel and collaborators, in where the gas cannot easily penetrate down to the disk region to generate the disk. So higher mass galaxies have warmer, hotter CGMs around, and then it is more difficult for the gas to cool down to the disk. So the disk forms in a less slowly. So it's probably the total halo mass, not the bulge mass, the dependence here.
Okay, so I thought a lot about it, and what I showed here is the stronger correlation we have. So this time delay with the total bulge mass and bulge prominence, meaning that is the bulge component that is driving the evolution. We also cross-correlated each single parameter with the total galaxies mass, but the correlation was less strong. This is a bit tricky to interpret because some of the disks in these galaxies are very star forming. So probably the galaxies has not accreted totally its mass. So it can be a result in massive galaxies at later times, but we were not able to observe it. So the interpretation and the correlation between the total mass of the galaxy and this time delay is a bit difficult to make. What we know for sure is that the bulge mass is playing a very important role. I can also comment that the result for Khalifa in the local galaxies show kind of a similar trend for both the bulge mass and the galaxy mass, meaning that probably if you observe lower redshift galaxy where the galaxy is almost assembled completely, probably you can see what you are describing. But for our galaxies, the correlation with the total galaxy mass is less evident.
Very interesting. And in fact, there is another parameter here that is the correlation between the bulge mass and the supermassive black holes mass in the center. So also the AGN activation, how this plays a role or not with the heating up the CGM. So it's probably a lot more to understand here and a lot more to plot and see correlations here. But very, very interesting. Nice. Thank you, Luca, for the talk and the answer also. So if nobody else has an additional question, we will leave it here. Again, thank you a lot for the presentation. And I invite everybody for the next week IPARCOS seminar that will be the last before Christmas and will be driven by Loic Hausmann from the Switzerland laboratory, APHL laboratory in Switzerland. And he will talk about the galaxy formation and evolution for the dwarf galaxies using cosmological simulations. So thank you everybody for coming today. Thank you, Luca, for accepting the invitation and for the very nice talk, and see you next week.
Bye.